Our first speaker is John Legault. The title of his talk is Regional Airborne EM Magnetics in the Selwyn Basin, an Explorer's Perspective. Jean has been a mineral exploration geophysicist since 1985. He obtained both his BASc and MSc degrees in applied geophysics. Right now he's Chief Geophysicist of Interpretation for Geotech Limited, which is an international airborne geophysical service company based in Aurora, Canada. He specializes in passive and active source airborne electromagnetics and their geological interpretation.
Thanks, Bob. Hi, good afternoon, everybody. As a preface, this is my talk. As a preface, I just wanted to say that this is actually a talk that was produced by Rob Carne at ATAC, Richard Phillips, and Julia Lane. I actually presented this paper at the SEG GEM workshop in Chengdu. So they presented it's based on a presentation given by Rob. He never produced a physical paper, and I produced the physical paper. So my second authorship is based on my contribution to the GEM in Chengdu, not the talk itself. Obviously, I'm going to have a lot of my influence on the talk is going to be there. Essentially, this is a talk given by Rob Carne in an evaluation of airborne, a ZTEM airborne EM data set that was collected in the Selwyn Basin in 2008, and it was recently released in 2013. So Ken Witherly had presented, the geophysics the geophysics of the survey. And what Rob did was his approach was, I'm going to analyze this from an explorer's perspective, so kind of like a non-geophysical talk. So it's odd, I think it's ironic that I'm giving a non-geophysical talk to, there's geophysics in it, but it's not to a geophysical audience. And on Monday, I'm going to be giving a geophysical talk to a geological audience. So anyways, that's the difference today. So anyway, I do want to thank the primer author, Rob Carne. This is his presentation. So here's an outline of my talk. After I introduce, I'm going to just give you a brief background on the ZTEM system. I'm going to talk about the Selwyn Basin geology, and I'm going to show the correlation between the magnetics and the geology, ZTEM and the geology, and the ZTEM ore deposits and mineral occurrences. And I'm going to skip to why I thought this talk was interesting is my talk on Monday is basically going to be on airborne EM applications for epithermal gold deposits. And when I was asked to produce because the GSN had asked me to present a paper on that, so that's what I did. And then when Brendan asked me if we would present an airborne EM talk here, I said, well, I've kind of run out of bullets. I don't have anything with a Nevadan or Western Corridor theme. And then I thought of this presentation by Rob Carne, so I decided that I would present it again to you today. But anyways, he shows a link between Yukon and Nevada, which is kind of interesting. And I'm going to show some Yukon skarn comparison and with the BC porphyry to see how they're similar and how they're different. So just before I start, I've been working with ZTEM data since I arrived at Geotech 8 years ago. It's hard to believe it's been 8 years. I was 18 years with Quantech and now 8 with Geotech. It's hard to see the time fly. But I've been talking, and I basically use the same setup. So for those of you who have seen this before, my apologies. But for you in the audience, I felt that I needed to at least describe to you what ZTEM was, what AFMAG means. AFMAG is short for audio frequency magnetics. It's actually an EM technique, not a magnetic technique. It was first proposed by Ward in 1959, and it was used commercially until the 1970s. So by the time I got to university, AFMAG had come and gone. And it basically remained dormant until early 2000s when Geotech decided to restart their airborne AFMAG. But that's the airborne McFar AFMAG system in 1959. The reason why they liked it in AFMAG in 1959 was it didn't use a transmitter. But anyways, it's a passive EM technique. It's in the same family as audio magnetotellurics. but we're only measuring the magnetic fields. So we measure HX, HY, and HZ. We don't measure the E fields, obviously. ZTEM is a variant of AFMAG, where we only measure the HZ field in the air, and we measure the horizontal fields HX and HY at a fixed base station. This was first introduced by a paper by Lowen Zhang, and Bob was standing right next to us. That was his first paper on ZTEM, where it was introduced. The EM sources are natural EM fields from lightning strikes, not ionospheric currents, it's just audio. And these come from equatorial thunderstorms. That's just an image of where they're centered, but basically you don't need to have a lightning strike on your property. The energy from these thunderstorms propagate, and they're a source field that we measure. The basic principle is just imagine a current's flowing along the ground. If you meet up with a lateral contrast, it causes the field to tip vertically or downward, depending on whether that's more conductive or more resistive. And that secondary EM field is called the tipper. That's because you're tilting or you're tipping that field. That was coined by Ward in 1959, but it's also known more formally as the Weiss-Parkinson vector. So the relationship between the horizontal and vertical field is really, normally in the absence of, in 1D Earth, in the absence of any lateral contrast, there is no vertical field. But when that vertical field is created, it's actually due to the interaction of two orthogonal horizontal fields. It doesn't matter what direction they're in, but that equation describes the interaction of those two orthogonal magnetic fields with the geology. And kind of like these operators, WZX, WZY, those are the tipper vectors, and that's how we solve it. So we actually determine that tipper vector by doing fast Fourier transforms of the time series that we measure, and we just solve this very simple equation. This is the ZTEM system. What it looks like, it's a helicopter. This is from Portugal. What distinguishes it here is a really long tow cable, 90 meters. A typical time domain EM system is about 30 meters. So it's because we're measuring passive EM fields, we've got to get away from the rotor noise and as much as far as possible as we can. So 90 meters is a very long tow cable. That's the receiver there. It's actually 7 meters across. It weighs almost 1,000 pounds on the hook. So it's the size of some of the like the Aerotem system. It's probably actually larger. This is the base station receiver. In this particular model, all we're trying to do is measure the horizontal fields in two directions. This particular one is slingable. In terms of transmitter, there's none required. We measure the vertical dipole at the receiver. The base we measure at a fixed base. We measure horizontal dipoles. We measure 6 frequencies in the 30 to 720 hertz range. We derive the inline and crossline tippers, and the noise floor is roughly 1%. And why that's important is it's similar to what we obtain with ground MT sites. So the big aspect of ZTEM is we're able to penetrate quite deeply. It's almost 1 to 4 kilometers for a 1 kilometer hose, which is quite resistive. But even in more moderately resistive terrains, the maximum depth of investigation is 1.5 kilometers, which is really significant. It's much deeper than any other airborne EM system. And even here, even though in a 10 meter host, where our penetration is diminished significantly, that's still, at least twice as much of a typical time domain EM system. So really, the takeaway here is ZTEM is a variant of AFMAG. We only measure the vertical field at the receiver, and we measure these horizontal fields at a reference site. And that's the reason for that is it improves the signal noise. Obviously, if you're doing a ratio of vertical to horizontal fields, if you're flying a system in the air, it's going to be vibrating due to wind shear. Those horizontal fields are not going to be well estimated. So by putting them at a base station, you just improve your field ratio. ZTEM maps resistivity variation to great depth based on lateral contrast. So you've got to have a lateral contrast. It doesn't, you can't, when there's no lateral contrast in 1D Earth, it doesn't see any lateral contrast, so there's no field. This is just to compare, and this is slightly different than the image in your booklet. The image in my booklet, I'm comparing the ground MT tip. This is ground MT tipper data. This is inline in phase, inline quadrature, crossline. Inline quadrature. I'm sorry, everyone, I'm sorry. This is inline in phase. This is cross-line in phase, inline quadrature, cross-line quadrature. This is how you would look at MT data. And in fact, we've got the MT tipper data plotted as those black crosses here. But in purple is the ZTEM data. You can see there's a really good correlation between the two. In fact, they match really well. And this is a image of this is a study done by and published by Hubert et al. At the SCG in 2013. She's from the University of Alberta. This is a ZTEM tipper image. This is the ground MT tipper image, and you'll agree they're almost, well, they're nearly identical in amplitude, and the only reason why is there's a sampling difference between the two. The ZTEM is actually better sampled than the MT, and that's why there's a difference in the contrast. So really what she showed was over this, and this is an epithermal, there's this kind of like lineament that you see here, that's a conductive zone relating to an epithermal gold deposit in British Columbia. And what she found was over 32 sites, the average was within 1%. So ZTEM, the fact that you can measure tipper data from an helicopter flying 80 kilometers an hour, 50 meters above the deck is amazing. But this is, to my knowledge, is the first time they actually, I've seen a lot of comparisons between NT models and ZTEM models. This is the first time we've actually shown the correlation between the tipper data. And this is, with tipper data, we can derive geological images. This is an extract of the survey from the Selwyn Basin. This lineament, kind of like you can see there's a conductive lineament here. That's a shale horizon, along which the Howard, it's a 200 million ton SEDEX deposit at Howard's Pass, and that's what it looks like. Vertically, this is, horizontally, this is 8 kilometers, and vertically you're looking at top to bottom 2 kilometers maximum here. So really impressive depth of investigation. Let's get to the talk itself now. ZTEM is, the Selwyn Basin is a large northwest trending Paleozoic sedimentary basin that extends 1,000 kilometers from Alaska to northern British Columbia. It's best known for its world-class SEDEX deposits, including there's a giant SEDEX deposit at Howard's Pass that has 180 million tons in proven reserves. In 2008, we flew a 25,000 kilometer area of the Selwyn Basin for a company called Exploration Syndicate, which was a private mining company. And that's the ZTEM survey coverage here in Yukon. In November, the Yukon Geological Survey released the data to the public. And these data were compared to the known geology and mineral resources and analyzed from an explorer's perspective by Carne in 2013 at the Yukon Geological Survey AM workshop in Whitehorse, where I was at. And Ken Witherly also presented these results at the PBAC in Toronto. So, and the analysis of that study is what we're presenting here. This is that's where Yukon is in Canada. This is the Selwyn Basin. You can see it takes up a big chunk of Yukon and part of the Northwest Territories, and that's our survey. The AM magnetic survey areas actually took a big chunk of both. It was, like I said, it was flown between May and October. We flew with 2 helicopters, and we flew almost 25,000 line kilometers at 1 kilometer line spacings. We acquired ZTEM data, the inline and cross line at 5 frequencies, including 360, as well as the total field mag. And it's actually one of the few publicly available data sets, AM magnetic data sets in Canada. In fact, you can download the data set along with a variety of it's not just the raw data, but Ken Witherly and his group also provided other information. This is what it looks like. I was talking with Frank earlier today, and he said, why don't they show the lines above the data? Well, these are all the survey lines. These are a kilometer apart. Some of these are 90 or well, they're almost, some are 150 kilometers long. It's very, very long survey lines. And that's why, and you can see that area is 200 by 200 kilometers. So this is a really, really nice data set. Like I said, it's free to download. In terms of the basin of the geology of the Selwyn Basin, it's a shale basin, but the Selwyn Basin occurred in 4 main stages. There was the Selwyn Basin that occurred in the Neoproterozoic, Lower Paleozoic as a passive margin. Then in the Lower Devonian, there was a turbidite basin formed. In the Mississippian, there was a clastic shelf that formed above it. So this is where the Selwyn Basin is. This is where that turbidite basin is above it, and above that, here's the Triassic shelf. And during the Corleone orogeny, there was deformation, intrusion, and metamorphism. And the synthetic mineralization occurs in the oldest units, and there's formation of lead, zinc, barium, copper, and gold, and minor gold, silver, I'm sorry. And the younger intrusions later on developed during the Mesozoic Corleone orogeny, and that's where you had gold forming, tungsten, moly, silver, and copper. This is what the Anvil district, there's a famous setics district called the Anvil district in Faro, and there's 5 deposits there. They're all mined out. But this is the Howard's Pass mineralization. You can see this banding, so you've got like lead zinc mineralization banded within that unit. And yeah, there's 400 million tons of ore there. The other type of mineralization is these intrusions that occurred during the Cretaceous. So this is the geology map, and just, this is, imagine though, these are like flatline units. So the ore division to Devonian sediments, right, everything in blue, some of this brown. And the Selwyn Basin is a deep Paleozoic basin. It's mainly composed of ore division to Devonian black shales and cherts. So this is a stratigraphic map. You don't really get a sense. You think of these units are piled on top of one another. The geology is largely flat line. So it doesn't really give you a sense of how the geology is divided down at depth. The Selwyn Basin were then metamorphosed and deformed during the Mesozoic, and that led to Cretaceous intrusions. And that's what these little brown, these are intrusive events. But except for fault and thrust deformation, the Selwyn Basin is well preserved. So this is a DM model ingratiated. This is now the presentation by Rob Carne, and he just shows the outlines of the granitoid intrusions, and these were taken from the Yukon Geological Survey mineral record. So he just plotted them on. He wanted to. This is the mag. It's not corrected for the. Okay. At any rate, this is the total field mag image, but you can see here there's a regional trend. It's the international. The IGRF, it's not IGRF corrected, so this is due to the Earth's field, not the geology necessarily. But if you were to see basically you're seeing there's not a lot of, except for these anomalies, there's not a lot, these anomalies are all due to Cretaceous intrusions, as shown here. So the rest of there's actually not a lot of action going on here because the sediments are non-magnetic. And they're so thick that you don't see through the basement. So basically, these granitoid intrusions are all you see from the mag. And what's interesting is you can see. I'm sorry. I'll go back. You can see here. There's these metamorphic. The intrusions themselves aren't magnetic, but the aureoles around them are due to hornfels. And it's explained. The geologist Moynihan just explained that actually the hornfels thing causes pyrrhotite to be developed in the rocks. And so this is actually magnetic pyrrhotite that's causing the mag anomalies. The intrusions themselves aren't magnetic. Sometimes the hornfels aren't manifested all the way around, but all of these magnetic anomalies are due to the intrusions, not the Selwyn Basin, not the results. This is now the apparent conductivity. This is from the ZTEM data, so now we're looking at ZTEM data. This was obtained by using it's actually not a VTEM transform. That's not true. It's used using a VLF transform of Beckett and Peterson. I apologize for that. It's a VLF transformation that converts tipper data to apparent resistivity. So this is the ZTEM tipper data, and you'll notice right away that we've got these nice bands, and you've got all of these circles in them. And lo and behold, those circles are the granitic intrusions. And what else is interesting here is the hornfelsing that you see that's more conductive. That's the pyrrhotite. So we see the aureoles from the tooth. And actually, that's just Jim Carne that just showed, like, what's interesting here is these, we're seeing the same thing that the mag is, but just differently. Rather than being a magnetic susceptibility anomaly, it's a EM anomaly. And if you compare to the geology, then that shows burden proof. This is where those intrusions were. Another thing that's interesting, he brought in the mapped faults from the Geological Survey record. And what's interesting here is, actually, if you go back, I just wanted to show this image. Remember that granitoid over here that didn't have the mag? It's actually got a nice EM image around it, right? Nice EM conductive image, which I thought was cool. These are the map faults, and you can see there's good correlation between the conductive zones and these map faults. And just take a look at this one. This is a map fault, and it shows how the conductive unit there is truncated right at that fault. And we didn't see that in the mag. And so what else did he do? He decided that he would put an outline around these conductive trends, and I'm going to show you why in a bit. So he decided to put an outline around these conductive trends that don't really appear to be related to the bedrock geology. There's nothing in the geology that explains those, at least the superficial bedrock. Then what he did was he plotted locations of all the mineral occurrences. So these are all the dots are mineral occurrences. And you can see right away the mineral occurrences. Some occur outside, but for the most part, they occur inside these conductive ZTEM trends. Again, wasn't seen in the mag. Next, he shows prospects. And what I'm going to show you is, I'm going to show you deposits in pink, drilled prospects, and significant showings in terms of geologic age. So this is Silurian. These are the oldest rocks, the oldest occurrences in the, not the oldest rocks, but the oldest occurrences in the basin. And these were all of the Silurian SEDEX lead zinc deposits. And this is where, these are all the deposits at Howard's Pass. Next, we're going to show these lower Devonian, so this is slightly younger, SEDEX nickel moly deposits. These are the prospects relating to Devonian SEDEX barite. And you can see, they all occur within these conductive units. He went to Upper Devonian, so younger SEDEX zinc, lead, barite deposits. These are the age of the McMillan Pass deposits. These are the Cretaceous skarn deposits here. Skarn tungsten deposits here. Cretaceous vein deposits here. Again, they lie within these conductive trends. These are the Cretaceous intrusive gold-related deposits. I'm trying to, they're up here, so they're outside the trend. The tertiary Carne type deposits, there's actually a gold deposit here, Carne style. And what he thought was interesting, he liked the trends, but as an explorer, explorers learn to look at trends and decide where they're going to start claiming to find similar ore deposits. You can see here, somebody's obviously seen the delineation here, but it's interesting how the claims are all within that conductive boundary. So what does it mean? Here's the Selwyn Basin geology. These are where all the deposits are situated. There's no, I mean, you could argue, yeah, they're situated within blue, but there's a lot of areas here of blue where there's no deposits. This is where now he's identified the conductive trends, and now we see that they're aligned along those, within those conductive trends. And what we know from the ZTEM, the results aren't near surface. It's a deeply penetrating technology. They're due to bedrock features that extend a kilometer or more below the surface, so they're not manifested in the geologic map. So how then can we relate the Yukon to Nevada North? And Ken also has this image in his talk, but if these trends are related to deeper basement structures, the alignment of the deposits are likened to the research of Earhart here at UNR that identified close similarities between the genesis of Carlin-type gold deposits in Nevada and the Yukon. So you see they're well separated. What's the link between the two? It's because they were both part of Rodinia. So here's the supercontinent of Rodinia, where future Nevada was, where future Yukon was. And from the map, you can see here how they were related at one period. It was that margin. And what Rob then said, well, we know that temporarily they're related. What about these mineral trends? We know, of course, Nevada has these important mineral trends. And he said, you know what? These mineral trends could also be a significant guide to exploration in the Yukon Basin. And I just wanted to show this image. This is a ZTEM image over a porphyry. This is the Morrison Hearn porphyry deposit. in British Columbia, and I'm just showing you what a ZTEM response looks over a porphyry deposit. These are Eocene intrusions that are at the heart of the deposit. And these are the zone resistivity. Basically, the potassic altered core is resistive, and the phyllic alteration on the outside is conductive. So these kind of like ring-like features are distinctive identifiers for porphyries in British Columbia. And that's about 2 by 2 kilometers. And this is the results from the Selwyn Basin. These are 1 kilometer lines, but you can see right away, these are the Cretaceous intrusions, and these are the orioles due to hornfels around these intrusions. And you can see how they're quite similar. So one is related to alteration due to porphyry, and the other is related to alteration due to skarn. I'm almost done. So in conclusion, we flew 25,000 line kilometers in the Selwyn Basin in 2008. We know it's well known for its SEDEX deposits, including the giant Howard's Pass deposits owned by Selwyn. The analysis of the regional magnetics highlighted a strong correlation between ZTEM and conductive trends and the mineral occurrences in the region, which weren't visible in regional mag. Because these are deep signatures, it had to be related to basement control, so it points to genetic similarities between Carne-style gold deposits in the Yukon and Nevada, where regional deposit trends are also well recognized. The similarities, and also showed similarities between the zone signatures of porphyry copper deposits in BC and Cretaceous skarns in the Selwyn Basin. And we think it underlines the importance of AEM in defining structural alteration trends in other areas of the Selwyn Basin and other areas around the world. And that's the end of my talk. And the takeaway from Rob that I liked was the trend is your friend. Thank you.
Thank you, John. We have time for some questions, comments.
Like I said, it's not my geophysical talk. I mean, I'd show you nice lineaments and nice, computer modeling, and it's what I liked about it was is from a geologist and explorer's perspective, how they would look at a large 25,000 square kilometer data set and dissect it, or try to find out where can I find that explorer's edge, where should I start exploring based on regional airborne magnetic data results. In this case, we would say, mag is great for that. In the case of the Selwyn Basin, mag was not great for that, unless you're looking for skarn-type deposits or contact-type gold deposits. In this case, the ZTEM actually proved to be a very airborne EM. Deep penetrating airborne EM was a good tool for regional geologic mapping.
I was going to ask, would you have seen or gotten the same results with just flying the ZTEM survey instead of ZTEM survey?
Well, that's a good question. Modern VTEM now, but back then the VTEM at best the maximum penetration would have been probably about 250 meters. So the ZTEM in the images that we're seeing are look below a kilometer. So it's hard to say. Like whatever's going on geologically that we see that's causing those isn't at the surface. It's buried. So yeah, the reason why they did ZTEM was they were trying to map regional trends at depth and below the ground cover. So maybe modern height like the ZTEM Max, although I don't know that you could fly in the topography there. And there's significant topography here, so if it was flat terrain, I would say yes, but if it was with this type of topography, that's going to be a tough goal for VTEM.
John, I would suggest that if you looked at the line spacing of the kilometer, VTEM, of course, is going to be the laser beam, and you're not going to have the line-to-line continuity, whereas the ATAC smears things out, and that was probably, we have a lot more geological coherency for what would never be considered a suitable line spacing for VTEM. Actually, AFMAG was in its stride, I think.
Well, that was the very first survey done outside of Arizona with the ZTEM system. So that was the very first commercial survey flown in Canada. So Exploration Syndicate, or the geophysicists there were very forward-looking, and that certainly, they said, we've got to fly a kilometer long lines. What's going to give us the best potential for deep structural mapping, and that was the ZTEM survey. Okay.
Okay. Thanks again.
Oh, Brendan. I'm sorry.
Sorry. So, John, the conductive trends, say that likely deep, what's the best guess as to what's causing it? Is it blood channels? Is it conductive fault zones?
That's I think it is, I think it has to be the shale units. They're going to be more fertile than the grits and carbonates for the type of mineralization that they're looking for, unless they're intruded. So I think you're right. It's got to be related to more shale-rich horizons within that stratigraphy, but it wasn't immediately obvious from the geologic maps. Thank you. Thanks, Bob. Thanks, everyone.